teaching fellowship at Smith College before then she migrated to a Hubble fellowship at UMass, and now I expect I shall be starting a faculty position at Williams College this summer.
Yes.
This summer, yeah. So she's been doing a lot of work on the physics of star-forming galaxies, and she'll be telling us about some of the clues we may learn today. So thank you, Anna. No, William and Mary.
Oh,
the other one.
sorry. They always get confused. Yeah.
Right, right. But it turns out we went to the same high school.
Yeah, we just found that out. Astronomy is a really small community.
We can sing the fight song later.
So thank you very much for the invitation to talk here. So my research, the main question that I'm looking at is how the universe became reionized. So reionization is one of the fundamental transitions that the universe experienced, but we actually don't know a lot about how it happened. So the universe, after the Big Bang, as protons combined with electrons, you had the IgM being mostly, predominantly neutral. But reionization was a signature of the effects of the first galaxies to appear in the universe. And so we think these early galaxies, the massive stars within them, produced ultraviolet radiation, some of which has enough energy to ionize hydrogen. It's called Lyman continuum. And we think that some portion of that Lyman continuum radiation escaped the bounds of the host galaxy into the intergalactic medium and began to ionize bubbles of the formerly neutral gas around galaxies. And these bubbles grew larger and larger, eventually overlapping until the entire IgM became ionized. We think this ended about redshift 6 or so. And so that's reionization, and the IgM has remained mostly ionized to this day. But there's a lot we don't know about how this exactly happened, and figuring out how reionization took place is one of the main questions that James Webb is going to try and answer. So if we want to understand the galaxy contribution to reionization, this is the equation that represents that. So it depends on three terms. This is just how many star-forming galaxies you have in your volume, and this is probably the easiest of these three parameters to measure. It also depends on then how many ionizing photons those galaxies produce. And then the most uncertain parameter is this escape fraction, escape. That's how many of those that are produced actually make it outside the galaxy. And that parameter is so uncertain, it's really uncertain even at redshift 0. And there's some tension depending on what IgM model you look at, whether we really understand how the IgM is maintained in its ionized state to this day. So we think star-forming galaxies can do the trick, can ionize the universe by redshift 6 based on constraints from Planck and the number densities of star-forming galaxies that we see. But you have to make some assumptions about escape fraction for this to be plausible. Namely, you have to assume that on average, each galaxy has an escape fraction of between 10 to 20%. You can fiddle with that a little bit if you boost the ionizing photon production, maybe get it down to 5%, but those are kind of the numbers that to keep in mind. However, more recent results looking at AGN found more faint AGN than we expected at high redshift. So there have been some arguments that no, you don't need star-forming galaxies at all. AGN can do the trick. But here you have to assume that 100% of the ionizing photons of these AGN make it out. And this is also tricky because the ultraviolet light we see from these galaxies with faint AGN is going to be a mix of star formation and AGN activity. So we don't really know what the relative contributions of star-forming galaxies and AGN are yet at reionization. Probably both play some role. Among star-forming galaxies even, we don't then know which star-forming galaxies actually are important for reionization. So there's some many arguments based on simulations and theoretical works that maybe outflows are some sort of precondition that you need in a galaxy to get your ionizing photons out. The idea being you've got a lot of supernovae, you clear out your neutral gas, and that provides these then low density channels where your Lyman continuum photons can escape. And so this might also scale with some galaxy properties, right? Your lowest mass galaxies may be more able to blow gas out of their low potential wells. Maybe having galaxies where with very high star formation rate surface densities, where the star formation and feedback effects are more concentrated, that might be, might enhance the effect of outflows. However, there are other arguments that actually maybe the lowest mass galaxies aren't as important as somewhat brighter galaxies. Because in your lowest mass galaxies, your star formation is not very efficient. So maybe those galaxies instead dominate. And all of this can also be time dependent. So the idea being when you have your young star cluster, when you have massive stars that are producing these ionizing photons, originally it's going to be born in neutral gas and shrouded, and then no Lyman continuum photons are going to escape. But if you wait a little bit, you're going to have the first supernovae going off in a few million years. You're going to have your massive stars start to evolve as Wolf-Rayet A stars. They're going to have powerful stellar winds that'll clear out their environment. And you may then have this optimal time of a few million year age when you can have Lyman continuum photons escaping. But if you wait too long, you've cleared out your environment, but all your massive stars have died as supernovae, so it kind of doesn't matter that you have these open channels because you don't have any ionizing photons to begin with. However, there's been some more recent studies that have suggested that maybe you can get more ionizing photons at late times based on the effects of binary star interactions, rejuvenating some of your population. So there could also be an age range that may play a role in Lyman continuum escape. And the reason that all of this has been so uncertain is that until very recently, we really didn't have any galaxies, or not very many that we could actually pinpoint to and understand, identify as Lyman continuum emitting galaxies and understand their properties. So ideally, you'd want to observe Lyman continuum photons at reionization itself. Just look at the galaxy population, which ones are leaking Lyman continuum. But unfortunately, the IGM gets in the way. There's just too much material going back to those great distances that no Lyman continuum photons are ever going to reach us. And so this is a real problem if James Webb's main goal is to study reionization, or one of main goals, in that we can't actually observe the photons that we need to identify those types of galaxies. So back in 2015, this was the state of affairs. Redshift 6 observations are impossible. So people have looked at somewhat lower redshifts to try and identify Lyman continuum emitting galaxies. And redshift 3 was pretty promising. We had dozens of candidates, and things were looking good there. But when they were followed up with Hubble, it was found that all but one of those galaxies were false positives, mostly due to contamination from low redshift galaxies along the line of sight that hadn't been seen before. So we went from several dozen to one known Lyman continuum emitter. And at redshift 0, we don't have to deal with that confusion, but despite many attempts to find Lyman continuum emitting galaxies, most surveys turned up empty-handed, just had upper limits or non-detections, and only 4 galaxies were known to have Lyman continuum escape. And you can see the escape fractions here. They're really low, just 1%, 2%. Some went back and forth in the debate as to whether it even was a detection or not. So we really didn't have much to work with to understand which galaxies could reionize the universe, because we didn't really find any that had escaping Lyman continuum at all. So there have been various proposals of ways you might actually find these elusive galaxies. As I mentioned before, outflows were thought to be one of the things that might matter. And so some people have proposed that if you look for galaxies with very compact, concentrated star formation, those galaxies may be more easily able to drive outflows, clear these channels for Lyman continuum to escape, so maybe you should target those galaxies. Another proposed selection, several proposed selections, deal with the neutral ISM around galaxies and its effects. So if you have more neutral gas surrounding a galaxy, they're going to absorb your Lyman continuum photons before they make it out into the IGN. And if you have more neutral gas, you're also going to see deeper absorption in low ionization or neutral gas species. So carbon-2 and silicon-2 have low ionization potentials. They coexist with your neutral hydrogen. And you should see weak absorption in those lines if you don't have as much blocking your source. More direct but more complicated tracer of the neutral hydrogen is Lyman alpha, and that's going to come up a couple times in this talk. It's one of the main tools that I use. So Lyman alpha is the 1 to 2 transition in hydrogen, whereas Lyman continuum is the energy it takes to take an electron from the ground state to infinity. And so like Lyman continuum, Lyman alpha is also very easily absorbed by any neutral hydrogen you have in the way, so it makes a good tracer. But it's a little more complicated than Lyman continuum. Whereas Lyman continuum is just absorbed, Lyman continuum resonantly scatters on hydrogen. So it's absorbed and then re-emitted in a different direction and has some complicated path out of the galaxy. But if you have less neutral hydrogen around your source, you should have less Lyman alpha scattering. And this can be seen by the effects on the emergent profile of the Lyman alpha line. So if you start out with a simple Gaussian profile, after it's processed through the gas by all these scatterings, you end up with, in the case of a static medium, these double peaked profiles. And the farther, the more scatterings the gas undergoes, the farther the Lyman alpha photons have to migrate from their original wavelength before they can escape. So if you have a very thick column of neutral hydrogen, you should see these weaker, broad Lyman alpha profiles. Whereas if Lyman alpha hasn't had to scatter very much, it should be strong and narrow. And anytime Lyman alpha scatters, it also increases the chances that it's going to hit a dust grain and be destroyed entirely. So you can also get, in the case of a large column, deep Lyman alpha absorption as well. So if you're going to look for Lyman continuum emitters, the idea is you should look for strong, narrow Lyman alpha, cases where it doesn't seem like Lyman alpha has had much difficulty making it out of the galaxy. And then the final proposed way of looking for Lyman continuum emitters deals with the structure of H2 regions. So here, if you imagine a Stromgren sphere, some very simplistic H2 region, your most highly ionized gas is going to be closest to your central source, and then you're going to transition to lower ionization gas, and then finally neutral gas. So in the case of oxygen, you would see O3, O2, and then O1. But again, if you have less material around your source, you might not see all of those states. So in this case, your gas doesn't fully go out to the Stromgren radius, your Lyman continuum photons are not being fully absorbed, some of them are escaping, and you don't have as much of these low ionization species. So you should see weaker equivalent widths of things like H beta, because you just don't have as much of it. And you should see ratios, such as a high O3 to O2 ratio, where you're deficient in these lower ionization species. So this latter case brings me to these green pea galaxies. So this is an image of a green pea. These were discovered in SDSS. You can see how they got their name. And the story of their discovery is kind of fun. They were actually discovered as part of Galaxies, if you've ever heard of that. So it's a citizen science project. And so members of the general public are asked to classify galaxies. And every so often they came across something that looked like this, and they had no idea what to do with it because it didn't look like any galaxy in their templates. And they started chatting with each other on the forums, calling these green peas. And actually, it was the general public that actually began to identify the selection criteria for these, and they're listed as authors on the original paper, which is kind of cool. It turns out that these are compact, highly star-forming galaxies. And the reason they're green is because this is their spectrum here. They're totally dominated by O3 5007 emission. And that shows up as green in the particular filters that were being used. And these galaxies have a number of similarities to galaxies at high redshift. But they're at lowish redshift, less than about 0.4. They're pretty rare in the local universe. So out of the several million galaxies with Sloan spectra, you're talking about maybe a few hundred or less of these green pea-like things. Some of the highest specific star formation rates in the local universe, lowish masses, very compact, as I mentioned, and metallicities of about 20% solar or lower, and again, dominated by these very strong emission lines. And so these are properties that are similar to some of the extreme emission line galaxies we're starting to find at higher redshifts. And another reason why they're green is not just because they've got this strong O3 emission, but they have weak emission in other lines, notably O2, 3727. And so the signatures in this spectrum say that this galaxy is very highly ionized. And so, we started thinking, well, maybe this is basically just a scaled up version of this H2 region cartoon, and we should look into these as possible candidates for Lyman continuum escape. And again, as I mentioned, these things are similar to high redshift, and it turns out that O3 to O2 ratio being elevated is also something that is we see as being increasingly common at high redshift. So this is looking at, here's O3 to O2 here. The gray points show galaxies from SDSS at low redshift. Green are the green peas, and then blue and red are galaxies at redshifts 2 to 3. So you see they kind of really occupy the same parameter space in terms of their spectra as higher redshift galaxies. And it seems like surveys looking at the evolution of this ratio of O3 to O2 show that it seems to be increasing at least out to redshift 4 or so. So again, these galaxies may have some lessons to teach us about some of the extreme emission line galaxies we're seeing at higher redshift, which may be more common than these green peas are today. So initially we wanted to look for other signs as to whether these green peas actually had escaping Lyman continuum. And unfortunately, it's pretty tricky to get Lyman continuum with Hubble. So we first did a case study where we just looked at those other signatures that we might expect, Lyman alpha and weak absorption lines. We looked at 4 of the most highly ionized green peas, and here are the resulting Lyman alpha profiles. We found 2 of them were really excellent candidates. These have very strong Lyman alpha, very narrow Lyman alpha, as we would expect if there's not a lot of neutral gas in the way. But these other 2 were not quite so promising. Weaker, this one actually is even in a deep absorption trough, so probably has a much higher neutral gas column than the others. And so we thought, okay, we've got 2 good candidates, 2 not so good candidates out of this sample of 4. Elena Henry has looked at a larger sample of green peas, and one of the characteristics that does seem to be common in this population is that they tend to contain a really high fraction of strong Lyman alpha emitters compared to your other low redshift star-forming galaxies. So there are indications that these galaxies are, again, similar to things at high redshift and may be deficient in neutral hydrogen.
Sorry, did
Yeah.
you say it's cost spectrum?
This is cost, yeah. And so similarly, we also looked at these low ionization absorption lines. And again, the same 2 galaxies, weak absorption, not really detected, and then much stronger absorption in the other 2. So it's painting a consistent picture that we've got 2 good candidates. And this was then confirmed in 2016. Izotov et al. Targeted 5 green peas and actually detected Lyman continuum escape from all 5. So if you remember the state of affairs in 2015, this was really, really huge. We immediately more than doubled the sample of known low redshift Lyman continuum emitting galaxies. These were the strongest low redshift Lyman continuum emitting galaxies, and it's the only sample that had ever been looked at where you had a 100% success rate of getting Lyman continuum. So finally we have a sample to start working with to answer these questions about reionization.
Excuse me, what telescope is this?
This is Hubble.
This is still Hubble?
This is Hubble. Hubble. This is looking, well, no, this was looking at Hubble spectra with cost. These are the acquisition images, but
The acquisition images, so those
Yeah.
are green or blue. Those are ultraviolet images.
these are ultraviolet images, yes, but not in Lyman continuum. They're near UV. Yeah. And so the detections, they found that indeed the ones with the stronger Lyman continuum did correlate with narrow Lyman alpha, as you might expect. So things were fitting together. That was promising. And since then, the field of Lyman continuum emitters has really exploded in the past couple of years. So another Lyman continuum emitter was discovered at redshift 3 that also seems to be green pea-like, enormous O3-to-O2 ratio, high escape fraction. More green peas were followed up, and again, Lyman continuum detected in all of them with a wide range of escape fractions, 2 to 72%. And additionally, then in just 2018, some stacked samples have been coming out at high redshift. And here too, it seems that samples that either have strong O3 or strong Lyman alpha seem quite promising in terms of actually having Lyman continuum emission. So we're just in the beginning stages of being able to work on these questions. So initially, it seemed quite promising that this O3-to-O2 ratio would be a great proxy for Lyman continuum escape. These were the data that had first come out in early 2018. But then as a few more points, so remember even in the sample of 4 that I showed, only 2 were actually promising candidates. And sure enough, as more data has started to come in, this is how this plot looks now. So it is true that as you go to this high O3-to-O2 ratio, you get a high fraction of promising galaxies. But it's not true that you can just take this ratio and then say, aha, this is my Lyman continuum escape fraction. There's a lot of scatter here. And so my work now has been looking at, okay, what makes this green pea population so special, and what makes, what accounts for the variation here, and what other maybe indicators of Lyman continuum escape could we use if O3-to-O2 isn't a perfect thing to look at. So I've been looking at a larger sample of green peas. These are selected to be the most highly ionized galaxies in SDSS. My new sample here is shown with green stars, and these are unfortunately a little too low redshift to get Lyman continuum with Hubble. So again, we're looking at Lyman alpha and UV absorption lines, other indicators. And again, these are the most highly ionized galaxies in SDSS. I'm going to point out this one up here in particular, which is not actually part of the legend, although it looks like it. This is J1608. It is the most highly ionized galaxy in the Sloan Digital Sky Survey, and it'll come up a couple of times. It's really an extraordinary object. So looking at the Lyman alpha profiles of these galaxies, ordered from by increasing O3 to O2 here, you can see that we have a large number of this characteristic narrow double-peaked profile. It seems quite common among this sample. But you also have galaxies with deep absorption here. So these are signs of a very high column density of neutral hydrogen. So again, we're seeing this variation in this population. Not all of these are good candidates for Lyman continuum escape. And J1608 over here has one of the narrowest Lyman alpha profiles ever observed, as you might expect from its very extreme ionization that we're seeing here. And these narrow profiles do seem to get more common as you go to the most extreme ionization. But we're still dealing with smaller sample sizes right now. So looking at J1608 a little more closely, the galaxy is extremely compact. Again, it's one of these extremely narrow Lyman alpha profiles, very weak absorption in neutral gas. So it's a very promising Lyman continuum emitting system, and just very extreme. So looking at this trend between the Lyman alpha profiles we're seeing and O3 to O2, again, it does seem like you get, as you're going to these very high ionization states, you get a larger number of galaxies with these very strong narrow Lyman alpha profiles. For comparison, these black stars show galaxies that have confirmed Lyman continuum escape. So anything below this red line is as narrow as confirmed Lyman continuum emitters. We don't know the Lyman continuum escape fractions for some of those others. But as you go to high ionization here, if you're selecting on that, you do get a high fraction of galaxies with these narrow Lyman alpha profiles. So what is it that makes the green peas so special? Well, so I started looking into this several years ago. One of the things that I was looking at was, well, do they have these signs of this optimal age that I talked about earlier? And if so, we'd expect to see signatures of these Wolf-Rayet stars and of supernova explosions. So in terms of Wolf-Rayet stars, we do see, this is helium-2. This is a nebular emission line that requires a lot of high energy photons to doubly ionize helium. So, and it can be produced by Wolf-Rayet stars. We also see in this, you can barely see it here, some nitrogen-3, maybe a little bit of broadening in helium-2. Those could be stellar features from Wolf-Rayet stars. They can also be produced, all of these features can also be produced by very massive stars, which would be apparent at younger ages. And very massive stars is the actual official term for those stars, and it's any star with a mass in excess of 100 solar masses. And we did also think we saw signs of supernovae too. This is work done by Ricardo Emery, and he looked at the emission lines of these green peas and showed that they have very complex kinematics and broad wings that he argued were from expanding supernova remnants. So I thought, okay, this is all holding together from what I expected. We've got Wolf-Rayet stars, we've got supernovae, these galaxies are compact, it's what everyone predicted. This is how Lyman continuum escapes. We've got the right conditions to start feedback and clear out neutral gas. But, as you might have guessed by my use of the past tense, this is no longer what I believe. And the first clue that this was not quite right came when we started looking at this galaxy here. This is NGC 2366. As you can see by these exquisite images, very close to the Milky Way. And this region here is called Markarian 71. And it turns out that Markarian 71 has all the properties of the green peas. It just might be a little bit lower luminosity. And if you were to take NGC 2366 and put it at higher redshift, you wouldn't see this lower surface brightness part. You would just see a little compact glowing knot, just like the green peas. If you read, this is a Hubble imaging of Markarian 71 in various emission lines. So green is O3 and red is O2. And you can see that the region splits up into two knots. Knot A here is the one that really dominates the green pea properties, and it produces 90% of the ionizing luminosity in this galaxy is coming from this tiny little region here. O3 emission, I don't know if you can see it quite well with the projector colors here, but the O3 extends out basically as far as you can see. You don't see a transition here to lower ionization states. And we know from H1 mapping of this galaxy that this region is actually an H1 hole. So it seems likely that Lyman continuum would be escaping in this direction here. Here you do see a little bit of red. Here it does seem to transition to lower ionization state. So here this direction would be washed probably. And it has an enormous, this region has enormous O3 to O2 ratio, enormous O3 equivalent width, has the broad wings in the emission lines, whatever you look at, it looks like these green pea-like things. However, the weird thing is that not A is the youngest part of this galaxy, it's only 1 million year old. Not B is the one that has the Wolf-Rayet stars, that has cleared its environment. It's got this lovely shell that is blown out. And so this is the one that I would have expected would have been the Lyman continuum emitter, but it seems like this one is, and it still has a lot of gas around, is very compact. So we started thinking, well, maybe are these green peas extremely young? And yeah.
I mean, well, change that a little bit. I mean, just not A, of course, that's it's high. It's still cases in kind of H2 region where the Wolf-Rayet is blowing that out. Why wouldn't that be leaking?
It could be, and we don't, again, this galaxy is only 3 megaparsecs away.
Yeah, right.
So we cannot get Lyman continuum information.
Right, this whole thing is like a pixel.
For this.
For a real average galaxy. But
Right. So we don't know. We don't know which one is. But what's key here is that this is the thing that's the green pea-like.
Fair. Okay.
So if we're arguing that if the green peas, something special about them is associated with Lyman continuum escape, and this is the thing that is green pea-like.
It's the lighthouse.
Yeah, it's the lighthouse, or yeah. This, it could be leaking Lyman continuum, but it's not a green pea. So that connection is not
too
clear.
close to get a Lyman continuum detection.
Yeah, unfortunately. So yeah, that's the tricky thing with all these studies, is the ones that we can get Lyman continuum for are a little more distant.
Right.
The ones where we can study things in detail, we can't get Lyman continuum for. So you have to try and maybe piece these things together and hope to get a coherent picture.
You wait long enough, the expansion.
Right. Yeah, so J1608 also shows signs of an extremely young age. These are is a stellar feature in the UV spectrum, and it's best fit by a model of 1 million years old. This is and as are these gas lines here, seen in emission, are also only seen in photoionization models where you have an extremely young age. J1608 is probably the most extreme case. It also has extreme H-alpha equivalent width associated with young age. But we're finding in any spectral features we look at, the green peas tend to show extremely young ages, maybe not quite 1 million year old, but maybe 3 million years old. And they're, in terms of their dominant young stellar population. So young ages do seem to be a really ubiquitous feature of these galaxies, and probably explain why you're seeing such extreme ionization. This is looking at some images of the green peas. Kind of see again, red here is showing the continuum, green is showing O3. And again, we're usually, sometimes you can see more extended structure. There's a continuum emission that goes all around here like this. There's some tidal tails in this galaxy and a couple of knots. But the O3 emission seems to really be coming from one star-forming region. So these really are analogous to Markarian 71, where you're dominated by that spectrum just of this young star-forming region that's really shining in all of this ionized light, and you might have an older stellar population, but it's not contributing as much to that really bright spectrum. And one thing, if these galaxies do have such extremely young starbursts, one characteristic that you're going to have to think about at these youngest ages is the ionizing radiation production itself, because that's when they're going to be at their peak production. They're going to have all of their massive star content. These very massive stars that I mentioned, I'm no longer thinking that those may be Wolf-Rayet features. Now we're starting to think they might be very massive stars. And those put out a lot of ionizing photons. And there have been signs, people looking at the green peas are finding that they do have this really high ionizing photon production. And this can also explain why they're so commonly seen as Lyman alpha emitters. So this is Lyman alpha equivalent width here and Lyman alpha escape fraction. And colors showing H alpha equivalent width. And since both H alpha and Lyman alpha are recombination lines, they tend to, they should start out in the same ratio. And then Lyman alpha will be modified by however much gets scattered and destroyed, but H alpha will just go out. And so what you can see is out here, some of these galaxies at the very highest Lyman alpha equivalent widths, especially ones with the slightly lower Lyman alpha escape fractions, started out with really high equivalent widths. They have very high H alpha equivalent widths. They started out with a lot. And so maybe even though you have some of it being scattered or destroyed along the way, you end up with a strong Lyman alpha signal at the end because you had so much to begin with. And I think that's something to think about with Lyman continuum as well, that if these are producing so much, you don't even necessarily need that high of an escape fraction to get a strong signal in the end. So what about outflows? This was really a common scenario that most theoretical works were looking at, saying that this is how you should get Lyman continuum out. And we saw these broad wings. However, you also see these broad wings in Markarian 71, not A. And it turns out this has been a decades-long puzzle going back to the early 90s, with debates as to what causes those wings. And it's not immediately obvious that they're from supernovae. In Markarian 71, people have argued there might be some electron scattering process or a cooling wind or various weird scenarios that have been proposed. But we can't just see these same features in the green peas and say it's supernovae. It's still an unsolved mystery. And when we look at velocities in other lines, we can look at those absorption lines in the green peas and measure their gas velocities. We actually find that the velocities we're seeing are really quite slow. So this is looking at, this is how narrow your Lyman alpha line is, and this is how weak your absorption is. So galaxies with narrow Lyman alpha or weak absorption, these are good candidates for Lyman continuum escape. And this is showing how highly ionized they are. So our good candidates here and here, they generally show slow expansion velocities in their low ionization absorption lines, not fast gas motions. So we're really not seeing the signs of enormous outflows that we might have expected. And this yellow point, of course, is J1608. Again, its absorption lines are basically consistent with 0. So it really does not have outflows, or not strong ones as far as we can tell.
These are low ionization gas.
Yeah, you can see the same trend shows up in high ionization gas as well. Yeah, so it doesn't. We don't see the signs of outflows that we would expect. And John Chisholm has done work looking at the confirmed Lyman continuum emitters and finds the same thing. They don't have outflows that are any stronger compared to other galaxy populations.
They're still detected, or they're just weaker?
You still see expansion. So this, for instance, right, it's less than 100 kilometers per second here, but it is a net blue shift. But there doesn't seem to be.
The lines like the equivalent of the line that are going down as you get higher up this one.
Yeah, so these are, this is the equivalent of the line. So these, will have weak absorption lines, not necessarily in the high ionization lines though.
Okay.
So in the low ionization lines, they're weaker, and we've thought about maybe some of the biases that might entail. But again, they show up in the high ionization lines too, so it's a pretty consistent picture. So one interesting thing too with Markarian 71 and with any of these extreme starbursts is actually the idea that they have weak winds was expected theoretically. So in these dense environments, especially when you have low metallicities with weaker stellar feedback, you maintain your dense gas longer, and that dense gas actually undergoes catastrophic cooling because the cooling goes as density squared. And so what happens is your energy, in an energy-driven wind, ends up getting radiated away, and you're not actually able to form a super bubble or something like that. Instead, your gas stays around, and so you end up keeping it longer. You don't see outflows. In Markarian 71, we have CO observations, and it hasn't cleared its environment yet. There is still CO right on not A, as you would expect if it's young and if it's not been able to, with the stellar winds, drive a strong feedback yet. And the CO also seems to be expanding only at 11 kilometers a second. So you're not, again, these are not the objects that have cleared their environment yet. So one thing then that if this is the case, if these galaxies are actually extremely young starbursts, then if it's not outflows, what is it? What can let Lyman continuum escape? So I think there are a few things that we need to think about. One is, as you mentioned, Casey, not B. So it's interesting that not B and not A are right next to each other here. Not B has had feedback, and could be responsible for clearing out a lot of this space, pre-clearing it, so that then the burst here that has all the strong ionizing photons can take advantage of the sight lines that have been cleared by a previous generation. And so we need to think about, in these regions, the previous star formation history and whether different clusters can help each other. Ionization itself is something to consider. So again, these may not be at their peak supernova feedback, but they are at their peak ionizing photon production. And they may be able to ionize whole channels of neutral material, especially ones that are maybe lower column density because they've been previously affected by feedback. So that needs to be something that's taken into consideration. And then you can also maybe turn some of that gas into stars and get rid of some of it that way. So from Markarian 71, it seems like it has a very high star formation efficiency based on the ratio of star formation to CO that we see. And we don't really know how efficiently these extreme clusters like this form. And it could be that if they're maybe also able to consume some fraction of their neutral gas in the star formation process. And that could also play a role at young ages. So I've also started looking at then, as I mentioned, the neutral gas in these galaxies. And starting out, trying out what that gas is doing, this is what's actually going to affect the Lyman continuum. So we have H1 observations so far of J1608. I hope to get H1 observations of more of these galaxies. So H1 in J1608 is a non-detection, actually. But it's an interesting non-detection. This is surprising. So compared to other galaxies of the same star formation rate, looking at H1 scaling reticulations based on what we would expect for a galaxy of this mass, the star formation rate, we should have detected H1. We should have easily detected H1 if it were there. It might still be there, but so J1608, the H1 limit we set is something like 10 to the 8.1 solar masses, and that's not crazy for a galaxy of this stellar mass, that amount of H1. But it is really anomalous for a galaxy with its star formation and blue colors. So basically what ends up, the end result is that this galaxy is really anomalous in its ratio of star formation to H1. So this is J1608 here, this limit, and this is comparing to galaxies with H1 data from alfalfa, dwarfs, blue compact dwarf observations, galaxies. I think these are galaxies in alfalfa and with SDSS information. And alfalfa is the Arecibo H1 circuit. And then these are, interestingly, the other 2 points that are anomalous here are 2 other confirmed Lyman continuum emitting galaxies. So we only have 3 data points on this plot so far. Hopefully we'll get more, but it is striking that these are so anomalous here. And I think there could be a couple of reasons for this. As I mentioned, gas consumption might be, this galaxy may have a very high star formation efficiency. Another possibility is that our star formation rate indicator isn't quite right because we're assuming continuous star formation, and J1608 is probably a 1 billion-year-old instantaneous burst. And so that could artificially boost it up here. But basically, I think the takeaway is then to think about this is really the ionizing luminosity of this galaxy. So it's got a really high ionizing luminosity to H1 content. And that could be a possible characteristic of Lyman continuum emitters.
I mean, if you've got some old star formation, all the gas, you've got some remnant of really high ionization star formation with so much gas left.
Yeah.
So if you're catching this at sort of this tail end of the gas consumption
Yeah, you could be.
phase.
It's entirely possible, yeah. We would need to do more work, I think, on these, especially the star formation history, not just the immediate burst. And I don't know what the past star formation history was for this galaxy. So we can also get information from Lyman alpha. So Lyman alpha, as you've seen before, this is this nice narrow profile, and it would also suggest that there's not very much gas around. But when you zoom in, you actually see Lyman alpha in absorption in this galaxy. So it has some component here that's narrow that would suggest not much material around. You also then have this higher column density signature from absorption. So what's going on? Does it have it? Does it not? This actually tends to be the case for a lot of these green peas in this sample. We see, when we zoom in, we see underlying absorption. And some of them, as I mentioned before, show pure absorption. Others show weak absorption with some narrow emission component together. And a grad student of mine, Jen McKinney, has done fits to this and derived the H1 column density that this Lyman alpha predicts. And it's several orders of magnitude higher than what would be needed for LIME continuum to escape. So again, we've got maybe conflicting information here, but I think it just, all it's telling us is that the gas here is really inhomogeneous. Right? We saw this in Markarian 71 too, that we have one sight line that's cleared and one sight line that's blocked. And we're basically seeing the same thing here. We're seeing information from different paths, where some Lyman alpha photons are making it out easily, others are absorbed. And there's a really high contrast here between the channels that are free and the channels that are that have high column densities. So again, as it fits together with this idea that these galaxies may not have completely cleared their environments and may still have a lot of neutral gas around, especially if they're extremely young, but they have some channels that are cleared out. And in terms of those channels, so we can also fit to the low ionization absorption lines and derive the covering fraction of this low ionization or neutral gas, and Jen did that. And interestingly, this correlates extremely well with Lyman alpha escape fraction. So we're looking at all the different things that correlate with these Lyman alpha properties. And other than Lyman alpha equivalent width, the best correlation for how much Lyman alpha makes it out is this covering fraction. And so this is basically telling us the porosity of the gas matters, that if you've got more holes, Lyman alpha makes it out more easily. So that would make sense. Presumably, Lyman continuum makes it out more easily as well. But this is not obviously the complete picture, because if this little cartoon were accurate, Lyman alpha we would just see Lyman alpha. We wouldn't see these complicated profiles. It had to have scattered somehow. So we also looked at what correlates with those double peaks that we see. And there, it seems like ionization is one of the things that most matters for that double peak profile. So the ones with narrow Lyman alpha tend to have weak O1 to H beta, high O3 to O2, high weak S2 to H alpha, whatever lines you want to pick. They show signs of high ionization ratios in their ISM, or weak neutral emission from O1, or low ionization emission from S2 or O2, whatever ones you care about. And this fits with this scenario where we expect a very highly ionized H2 region, not very much neutral gas surrounding it that Lyman alpha scatters on. So we can combine these two cartoons, and this is probably, realizing that there are actual galaxies aren't perfect spheres. Instead, we've got basically some channels that are highly ionized, where Lyman alpha is making it out and not scattering very much. Other sight lines where it's blocked, where you're seeing absorption, and that's also creating low ionization absorption lines. And presumably these channels are what matter for Lyman continuum escape as well. The other surprising thing we found when we looked at what correlates with these Lyman alpha profiles is that metallicity was one of the strongest factors that correlated, as strong as the ionization. And this was kind of unexpected to us at first. So we thought about, what could this be? Thought, okay, maybe it has to do with the dust content. But it didn't correlate very well with measures of dust from the Balmer line ratios. So we thought, okay, maybe we're just seeing the galaxy mass metallicity relation. So lower mass galaxies have lower metallicities, and lower mass galaxies somehow have more Lyman alpha, or Lyman alphas escaping more easily. But it doesn't correlate well with that either. So we thought, okay, maybe it's a trend with the lower metallicity stars are producing more ionizing photons. But it didn't seem to correlate with measures of that production either. So one of the things we were left with was, well, maybe it's high ionization parameter itself. So these measures of ionization, like O3 to O2, have been known to correlate with metallicity for decades. It's not entirely been known why. But one possibility has to do with feedback. So in a high metallicity cluster, you've got your stellar winds, you end up blowing away your neutral gas into this shell of material, forming a superbubble basically. But at low metallicity, your stellar winds are weaker, and you're not as easily able to clear out your gas. So it sticks around, and it's at higher density, because it's staying. And that higher density gas tends to maybe become clumpy because of gravity. And this can cause that signature of high ionization parameter, of high ionization emission. You get this strong O3 emission because you've got dense gas really close to your ionizing source that's just being extremely highly ionized. And because the gas is so clumpy, it's also concentrating itself and creating channels that are lower column density. And so this is what, similar to the picture I was showing before, where we think we've got some channels where you've got absorption, other channels where you've got relatively low columns, and your Lyman alpha and Lyman continuum photons are able to escape. And yeah.
So speaking, I like this, so speaking spherically, you're kind of saying, assuming there's still kind of spherical models, what would be, high density, low covering fraction, high covering fraction, that would be high density, low covering fraction, or
Yes.
something. High
Yes.
integration parameter,
High density, low covering
low
fraction. Yes.
fraction, right.
Yeah.
There's a mechanism to allow that to form.
Yeah. Sorry, what did you say?
No, there's a mechanism to allow that to form.
Right,
Okay.
right. So this is also consistent with what we were seeing with the Lyman alpha profiles, where you're seeing high column densities and then low, the high contrast there. High column densities, absorption here, and then lower column density signatures from the other Lyman alpha emission. So we may need to think about then, in addition to these processes that I mentioned before, may need to add one, which is actually the fact that we have weak winds at low metallicity, and maybe have a clumpy gas geometry. That can also be one of these factors that might play a role in Lyman continuum escape. So, just to summarize what we're learning so far about the green peas, these are young, compact, highly ionized starbursts. And for the first time, this is the first population we discovered that where Lyman continuum escape seems to be a common property. So we can finally start learning about that. Surprisingly, it turned out young ages were key to this population, not the sort of optimal Goldilocks age range that I thought. Supernova feedback doesn't seem to be important, no matter how much we keep looking for that. So instead, it may even be the fact that feedback is weak, that you have these weak stellar winds and are maintaining your dense gas and then forming some clumpy geometry. That might play a role. Other factors, we need to start thinking about star formation history, star formation efficiency, and then the geometry of these galaxies too. So one explanation for this large scatter we were seeing in those scaling relations may be the fact that you've got this really high contrast between dense gas and channels. And depending on how something's facing, you may or may not detect it as a Lyman continuum emitter. But there's still a lot that we don't know. We don't know how exactly how similar or different these galaxies are with the high redshift populations. Are these the same thing? What properties might be different? What lessons can we take to us with us at high redshift? We also don't know whether this is the only Lyman continuum emitting population out there. So it could be that there are other populations where supernova feedback is important. We're catching these at a very young age, and that seems to be one population of Lyman continuum emitter. We really haven't surveyed the whole parameter space yet. And we also don't know still how we actually find these Lyman continuum emitters at high redshift. We've looked now at one of these proposed selections, the high 03 to 02, but as I mentioned, there's this whole slew of others out there. And many of these have not really been tested at all. This idea of looking at Reef equivalent widths has not been tested. The green peas are, they are compact, but there hasn't been a systematic survey of just compact galaxies. So some of these, how well some of these work is really unknown. And so that's why we are starting a new program with Hubble. This is a large program, the Low-Redshift Lyman Continuum Survey, cycle 26. And we have 134 orbits. We're getting 66 new low-redshift galaxy measurements of Lyman continuum, testing those various proposed selection criteria. And because we have such a large sample, we'll hopefully be able to test the effect of orientation on the scatter we see in these relationships. This will bring the total number of low redshift Lyman continuum measurements to 100. So we're finally going to actually have a real statistical sample to start looking for that. And we also have a team working on radiation hydrodynamic simulations that'll look at how how Lyman alpha is escaping from realistic galaxies and compare that with the observations that we have. And just showing this is the sample that we're looking at. These are X's show known detections, and blue is our new sample. We're going to be spanning a really wide range of 03 to 02, range of magnitudes. We're getting to low luminosity galaxies as well as ones above L star at redshift 8. And so hopefully, getting a diverse sample, more diverse than just looking at green peas, and to able to start to find out which populations in the local universe actually have escaping Lyman continuum. So hopefully more updates to come. And so with that, I'll take questions, and thanks again for inviting me. I'm working with Swara Rabindranath, and she has C3 observations of green peas. And yeah, so she's got a paper out and prep on that. One of the interesting things, so C3, like H beta, you would expect that if you have a density bounded situation where you're blinding continuum escaping, you'd expect the equivalent width to be weaker. But actually, we see in the green peas strong C3 emission, as we do in H beta other lines. And so really, it seems like because they're so young, they have really high C3, and that sort of compensates for what you might expect for a reduction. So using it as a diagnostic for line of continuum escape, I think might be tricky because you have to really know that age well or other things that might boost C3. Using it as a diagnostic for other things like age and ionization parameter and things like that might be more promising. That's the only line we've looked at so far. The other lines we mostly see are low ionization absorption lines, and that we'll test with the survey as well. Those absorption lines can be tricky because they're weak, and they're going to, at high redshift, you're going to mostly have access to them in stacked spectra. They're also helicity dependent, but yeah. C4, yeah, so C4, I don't have that for galaxies. We're hoping to get some in that. One thing is in some of these low metal C galaxies, you can often see it in emission as a nebular line. Yeah. I know Elena Henry has done some work on magnesium too, and that seems to behave like Lyman alpha, which is encouraging. It's another resonant line. Yeah, another resonant line, and it's and so it might be a good substitute when you don't have Lyman alpha with the IgM. So magnesium too could be promising.
When you start worrying about supernovae and low density environments, you have to realize that we don't know what those models are.
Yeah.
We don't know nothing about them, so you really can't rule out supernovae when you go into other metal density environments. We know so little.
Well, would you expect them not to drive outflows at all, or?
87A was totally unusual. For instance, it was much less massive. It has less kinetic energy.
Yeah.
So there are a lot of things. Things that can happen with different metals in supernovae. The models. Remember, the modelers can't even get them to explode. So there's a lot of uncertainty.
Yeah. Well, that too. I mean, so supernovae may happen, but it makes it then tricky for them to actually affect the neutral gas if they're not having a lot of kinetic energy, or if they're doing a complete collapse without an explosion, for instance.
Well, I like that more than 2 or 3 in low density environments.
Yeah.
I understand supernovae.
Yeah.
The other question is when you're monitoring the galaxy, just doing it by eye, the opening angle for the area that was figured out was about 90 degrees. That means that the solid angle is between 150 and 110 before it lies to radius.
Yeah.
So you have a clump of CO over here. You have an opening angle here. It's a small area. So why is the CO just not protected from any other direction like it is in Orion? It seems like there's a huge projection effect in your selection of these objects.
Oh, probably. There's probably an orientation bias, and that can also be why you tend to see Lyman alpha in emission, for instance, with these. I don't know. We don't understand opening angles very well with Lyman continuum emitters. We just know that we expect it to have a strong effect. And the simulation suggests that you need 50 or more galaxies in a sample to be able to get around that kind of scatter. Regarding the CO, we also don't know, so we see CO there, but we're limited by resolution there too. We don't know how, whether there are holes in that distribution of CO. And so there are, from low ionization absorption lines, there's some indications that Markarian 71 could be a leaker along our line of sight as well. But again, our image of CO makes it look like it's totally smooth. It probably isn't. And at smaller scales, we don't understand the clumpiness either. We don't know the opening angle. And that's something we're also hoping to look at more with simulations, and maybe also with the statistics of our larger sample, is whether we can set any constraints on that.
The CO in the Orion Nebula is well separated from when we see the star formation. So where you see CO doesn't mean that you know what's happening where the ionization is happening.
Right, yeah, they can be distinct.
You know they're separate, at least in one case.
Right. Oh yeah, so you think the CO might be completely unrelated to not A?
Well, the star formation propagates in one direction, often not in the other direction.
Yeah.
So you leave part of the molecular
so that
cloud
could be
untouched, And the other part.
Yes, so not A itself could have already gotten rid of its own.
You see that
CO.
Eagle nebula?
Yeah, it could be.
You see it ionized like this, and then
Yeah.
below is where all the molecular gases.
Yeah, we don't have a answer to that, other than, I guess velocity information might help somewhat, I'm not sure.
More questions? All right, well, hand us around the rest of the day. Thank you again. We're here for lunch. Did we schedule grad harassment for sometime? We're gonna do that. We did, okay. So that will.
Don't worry,
What?
it's fun.
We don't know which way the vector points. If it's
Okay.
harassing the speaker or,
Or the, yeah.
yeah. We'll let you guys sort it out.
What? The what?
Keep track, okay.